Testing, testing. Can you hear it? Can you hear me talk? There's a lot of like background noise though, so I don't know. If I could ask you to all take your seats so we can get started. Yeah. All right, good morning. So welcome to day 2 of IGC9. And this morning is the aerosol session. I'm Colette Heald. One quick reminder before we begin, a lot of folks have noticed some of the challenges with the audio. And so I'm reminding all speakers not to lean in because apparently that is causing problems. So just try and stay this kind of distance away from the mics. Okay, so with that in mind, I want to introduce our keynote speaker this morning, who is Anne-Marie Carlton from the University of California, Irvine, who's going to talk to us about decadal change of particulate organic carbon fractions.
Is this okay? I'm very nervous about getting too close to the mic. Thank you for the kind introduction, Colette, and thank you, Danielle, for having me here. I've heard a lot about the GeosChem meetings over the years. I've never been. This is my first time, and I'm very excited to be here. I'd like to acknowledge Amy Christensen and Justin Davis, who work as students in my group, and also Will Porter, who recently became my neighbor. He's from UC Riverside. Before I get started, I always like to provide context for our work. I've spent most of my life on the East Coast, specifically New Jersey, and I recently moved to California, where I've been working to develop a West Coast perspective on air quality. And I come across images like this one, and this one has become my favorite from Brave New Films. And the reason why it's my favorite, the first reason, is the gas mask. I think that that's a really nice touch. And whenever I hear someone talk about a low-cost economic solution to environmental problems, I think about gas masks and the gas mask lobby. And so the other reason why this is my favorite, and I want to say this to the young people, 1954, that's 16 years before there even was an environmental protection agency. The people who did this is your grandparents' generation, your great-grandparents' generation, and they took us from air that you could chew to air that looks like this. And they did it without Google. And they didn't have a calculator. If they did, it was probably the kind you could plug in. Okay, but yesterday at the meeting, we heard people talking about air quality issues in Asia. Eloise spoke about Africa, but it very much remains a domestic issue. And so in Los Angeles, there was more air quality violations in 2016 than there was in 2015. There was more air quality violations in 2017 than in 2016. And I checked, and it recently became official, there was more in 2018 than there was in 2017. And the reason how I found this out was my mom actually called me to tell me that. And she said, "What are you doing? You're obviously not helping." I need to go back to New Jersey. So we need your help fixing this problem. Okay, so we cannot use snapshots in time to robustly evaluate trends, but they are compelling. And they show us this dramatic improvement in air quality over the United States. And so the Environmental Protection Agency and the states, they promulgate rules to enforce the Clean Air Act. And predominantly from an air quality perspective, there was rules aimed at emissions of sulfur dioxide, and the impetus behind that was acid rain. And then an ancillary benefit was the decrease in sulfate particulate matter concentrations. There were rules aimed at curbing NOx emissions. Again, the impetus was to control ozone, and an ancillary benefit was a decrease in nitrate particulate matter. And recently, it's been noted that particulate organic carbon across the United States has been decreasing. This was first noted in regions such as the Southeast United States. And then David Ridley, when he was in Colette Hield's group, pointed this out for the whole entire United States. And this is really intriguing because there hasn't been targeted regulation at organic compounds. There's been things like fuel economy standards, but they're insufficient to describe what we're seeing with conventional wisdom. And so that's something I've been trying to work on. Now, yesterday at the meeting, some people were talking about intensive field campaigns like the SOAS campaign or Seekers or SENEX. And those intensive observation periods are really important for model development. Jing-Chu Mao wrote a paper about that, but they're sort of one-offs. If we want to evaluate trends, we really need to use routine networks and models. Those are primarily our tools that we have available to us for long-term trends. And so it's my ambition to get the right chemistry into models so that when we use them, it's not only that we're hitting the right number, but that the model responds appropriately when we test a policy scenario or a control strategy. Okay, so particulate organic carbon, everything that we measure is an operational definition. If you've seen a measurement person explain in excruciating detail about their inlet, that's why. So for when we say particulate organic carbon, we're talking about a thermal optical absorbance monitor. And so what happens is particles are collected on a filter, and then they're put into essentially an oven for some amount of time. And so when we have these TOC measurements, really there's different thermal fractions responding to different volatility. So for example, the temperature is held for a certain amount of time, organic gases come off, they're detected. Then the temperature is risen. Again, it's held for a certain amount of time, organic gases come off, and they're detected. In the 1990s, people argued a lot about the temperature. I call that the carbon wars. And the carbon wars ended in 2005. And now almost all the monitors use the same temperature definitions. And you could imagine you're making cookies, you put them in your oven, you start to be able to smell the cookies. It's because organic gases are coming off. If you leave them in a really long time, they eventually burn or pyrolyze. That's how I make them. So we're going to look at particulate organic carbon measurements in the improved network. So in this map, every single black dot represents a monitoring location. And then behind the black dots, you can kind of see these gray blobs. And these are areas that are considered to have similar chemical climatology. So the meteorology is sort of similar, and the emission sources in the area are sort of similar. And Improve says these are chemical climatology areas. So during the talk, I'm going to talk about Appalachia, and that's a specific gray block. I'm going to talk about West Texas, the Northwest, and the Northeast. Okay, so first things first. What I'm showing here is a difference from 2016 to 2005 in total organic carbon. The bigger the circle, the larger the decrease in TOC. We really like the Ridley paper, Colette, I was telling you yesterday, and so we made these plots just like yours. And so the bigger the circle, the larger the decrease. And there's one red circle where it looks like total organic carbon has actually gone up, but it's not statistically significant. So when we look at the different organic carbon fractions that are contributing to this overall trend in TOC, what we find is that the decrease in total organic carbon is being driven by the thermal fraction called OC2. And actually OC3 is increasing. OC1 and OC4 don't really show any trend over the last decade or so. And then what I'm showing here, the x-axis is time, the y-axis is the contribution of each thermal fraction to the total organic carbon. We're neglecting the pyrolyzed burnt carbon here, so they don't always add up to 100%, and that's why. But the bottom green line is the trend in OC1, OC2, OC4, and OC3. So that's very exciting. We think that we're onto something, that thermal fraction of OC3 is increasing in time and OC2 is going down in time. But hopefully you find that exciting too, but there's some unfortunate chemical reality. Okay, so NYSERDA is a New York state agency, and they did a series of experiments where they put single component particles on a filter and then exposed them to that OCEC measurement procedure. So this black line is a temperature trend, and it's not perfect, like that perfect step function in my idealized version. You can see this is temperature 1, temperature 2, temperature 3, temperature 4. This yellow line is succinic acid, and it's very well behaved. It comes off only as OC2. But that blue line at the bottom is oxalic acid, one of my favorites, and it's not well behaved. It comes off as 3 fractions. So part of oxalic acid comes off as OC1, part of it comes off as OC2, and part of it comes off as OC3. I hypothesize that that's related to the different protonation forms of oxalic acid. So the dianion would be the least volatile, and then the fully protonated version would be the most volatile. So there are these trends in the thermal fractions that tell us something. There's a lot of data. These thermal fractions have been measured at approximately 200 sites since 1988, and they tell us something, but there's a possibility that we might overinterpret them. Okay, so I got the GeoSchem logo yesterday. Thank you. And so I talked to Will, my neighbor, and asked him, could we use GeoSchem to maybe try to figure out what's going on? So what Will has done here is different summertime simulations with GeoSchem. The modeling details are on the bottom. The hotter the color, the higher the concentration. We sort of imagined that we had this thermal optical measurement technique inside the model and sampled it. And so what we see is in the Northwest, there's some strong interannual variability that's driven largely by fires. The concentrations are largest in the eastern part of the country. The Southeast United States is a little bit higher than the Northeast United States. Okay, so I'm comparing now GeoSchem with our measurements. In these stacked bar charts, the bottom is the thermal fraction 1, then thermal fraction 2, and thermal fraction 3, and then 4. And what Will is showing is the total organic carbon, and then what we estimate the total organic aerosol is, because organic compounds have more than just carbon. And so I think that modelers like you guys are always very generous towards the measurement people, like, oh, there's the right answer, and we're trying to match it. I consider this very, very good model performance. I don't know how you guys do it. It's pretty amazing. So there's been a decrease in Appalachia with time, and like I was showing you before, OC1 is decreasing a little bit, OC2 is decreasing dramatically, OC3 not so much, is actually getting larger. We find this also in the Northeast. The measurements are a little bit lower than in the Southeast. The model predicts they're a little bit lower than in the Southeast, and they have pretty much a similar trend. And again, if you look here, OC3 is growing, OC2 is getting smaller. Same thing with West Texas. The model is much, much lower. The measurements are much, much lower. The same trends in OC2 and OC3. So if we just look at the measurements in and among themselves, we see interannual variability in the Northwest. We see low concentrations in West Texas. We see higher concentrations in the Eastern United States. And the model has the same thing, the higher concentrations in the eastern part of the country, the lower concentrations in the western part of the country, interannual variability where there are fires. Joel spoke yesterday about the wintertime, so I made plots for the wintertime, same locations, and we see the same exact trends. With time, OC2 is going down, OC3 is getting larger. Okay, and then the other thing about organic compounds and total organic carbon, when we measure particular organic carbon, we're just measuring the carbon that's in that sample. But really, organic compounds have other atoms associated with them, oxygen, hydrogen, nitrogen, sulfate, even. And so there was a series of experiments done at improved sites, and I'm referring here to work done by El-Zanan, where they went to improved sites and then they measured organic mass to organic carbon ratios for specific sites. And so the way that they did that was they collected particles on a filter and then they rinsed them with increasingly polar solvents. So the first rinse was done with DCM, or dichloromethane, very nonpolar. And then they rinsed the filters again with acetone. Had I done these experiments, I would have then rinsed them with water, but they didn't do that. But water-soluble organic carbon will also come off. And then what they did was they measured that organic matter, and then they did the OC measurement technique, and they got site-specific OM to OC ratios. And they've done this a couple different ways. And we're using their best estimate. So what I'm showing here is circles on the sites where these OM to OC ratios were measured. So in the Northwest, they actually get an OM to OC ratio of 2.6. In the Northeast, 1.8. In Appalachia, 2. In West Texas, 1.6. And in the Colorado Plateau, 1.6. So the Colorado Plateau site in their study is no longer taking measurements. And so we're just going to look at these sites, these 4 areas where they're still taking measurements. And so when we look at the trends in particulate organic carbon versus the trends in organic mass, this is what we get. So on the left-hand side is from the measurements. The bottom green line is the sense slope. So it's a way to calculate a longer-term trend when you have seasonal variability. And then the slope that you would get if you do what's often conventionally done, where we take total organic carbon and multiply by 1.8. That's what's used in the visibility formulas. And then at these same 4 locations, if you account for the site-specific organic mass or organic carbon ratio, then you get this higher slope still. And then Will did that same exact thing for those sites in geochem. The bottom green line is the trends that he would get for total organic carbon, and the higher trend is what he would get if he uses site-specific OM to OC ratios. So the model is actually a little bit higher than the measurements, and I think that that's okay. If you've ever seen the improved samples, how they're collected, they can sit out in the field for several days, and then they're transported not in a cooler, and so I think there are a lot of losses. Okay, so what I hope you take away from this talk is that the rate and the spatial patterns in organic mass and organic aerosol decline or increase in some of the fractions is different across the country. The decline in total organic carbon is driven by the thermal fraction organic carbon 2, and we have no idea what that means. Organic carbon 3 has been increasing with time, which I find really, really interesting, but I have no idea what that means. And then one thing that is really remarkable to me is that geochem reproduces these trends no matter which way we look. going forward, the OM to OC ratio changes seasonally, and it's been changing in time. Jenny Hand has a really interesting new paper that shows that this changes. Spatial and temporal trends in geochem, I think there's some hints there for what might be driving those changes for the exact chemical reasons. I think geochem can give us some insights, but there's a chance that we might overinterpret that, but there's a lot of data, and so we're trying to balance all of that. I'm really grateful to, we use data from the Improved Network. I didn't talk about CSN. We use data from NAR. Hundreds and hundreds of people helped us do this, literally. I did none of it by myself. And thank you for making geochem so user-friendly. And thank you so much for having me and for your attention.
So Emery did a great job with time, so we have time for some questions. I saw May first.
Hi, Emery.
Hi.
That's great. In your geochem simulations, do you see the different SOA components having different variabilities?
I will agree to take the hard questions. So I haven't looked at that yet. And we would, we're planning to do that because it's, I think, the way to try to figure out what might be doing that, but I haven't looked at it in detail, and I don't think Will has yet either. But yeah, that's exactly where we're going.
Two related questions. One is, what is driving the different trends in different volatility bins? And second,
I have no idea.
and secondly, I think in geochem we assume an OM to OC ratio of 1.8. So I was wondering why there's a trend in that in geochem.
Why? Well, there would. Okay, you're asking about this one.
Right, the right one is geochem, I assume.
Yeah, and this is just total organic carbon, and then this is accounting for that OM to OC ratio. Yeah, yeah, and I'm just showing if you do it that kind of regular way, 1.8, or if you use the site-specific values, you get almost the same slope, but they're a little bit different.
What would you predict for the change in those volatility fractions? Just so if the VOC precursors, do you think they're the same except the non-SO2 trends?
I don't know. I had a lot of ideas until I found this appendix in the NYSERDA report. And so lots of compounds come off as more than one thing. And, this wasn't a filter with these different single compounds on it. This was one filter at a time with one compound. And so I think, so for example, oxalic acid will preferentially be in one of these forms depending on relative humidity. And so when they were conducting the experiment, that might have something to do with it too, when it comes off.
Very nice box. Thanks for. So I have a question for you. In the Southeast US, in the last decades, in some years we see droughts and we see significant amount of fires.
Yeah.
So why do we look at the trend of organic? The trend seems pretty smooth, declining with time.
Yeah.
So, have you looked at the seasonal basis? The trend, you see some fluctuations because of the
yeah, and maybe I should have shown that, but yeah, we do see differences in this season. So if you were to just look at the summer trend over years or the springtime trend over years, they're not the same. They're not the same.
Eloise?
As modelers, what should we focus on improving in our representation of organic aerosol? By priority.
Yeah. Okay. I guess it depends on the science question. So my favorite chemistry is cloud chemistry, and I think that changes the vertical profile of the organic carbon you would predict if you add chemistry in these areas where you have vertical mixing. If you want to hit surface mass, I think I saw you could just do CO2 to OC ratio or something like that. What science question would you want to?
I suppose if you showed you reproduce the observations very well, but we've got so much uncertainty in how we represent monoterpene SOA.
Yeah.
Glyoxal is a bit of a, a hand wave. Representation.
Yeah, when I showed the difference, in the OM to OC ratios, there was this really sharp contrast in humid areas versus dry areas. And I didn't really understand that. I always lived on the East Coast. And when I moved to California in dryuary, I was like, oh, this is a very different partitioning regime. And so in those areas where the ohm to OC ratio is really high, I think if I'm an organic gas, I'm much more likely to encounter liquid water than I am condensed organic mass. But in dry areas, that's not true. So I guess I have the idea that I alys have, and it's that water is important.
That's a great note for you to end on. So let's thank Andrew again. So our next speaker is Becky Alexander.
I'll fix this for you. You can see.
Okay, so I'd like to start by, let's see if I can make that go away. There. Oh, no, I'm not ready for that. Okay, so I'd like to start by acknowledging the person who did all the work I'm about to present, Jingwen Xiao, who's co-advised by Lin Zhang and myself. So we looked at the oxygen isotopes of sulfate during Chinese haze events to quantify the different production pathways of sulfate. So sulfate that is produced from oxidation of ozone results in a large O17 excess, around 10 per mil. Oxidation by hydrogen peroxide gives a small oxygen 17 excess, and everything else gives 0 O17 excess. So everything else includes gas phase oxidation by OH, transition metal catalyzed oxidation by O2, oxidation by NO2, and also primary anthropogenic sulfate. So we published the observations last year. We collected samples between October 2014 and January 2015, and on the left shows the observations of PM2.5 and sulfate concentrations on the top, and the sulfur oxidation ratio and the isotopes on the bottom. So the sulfur oxidation ratio is indicative of how quickly SO2 is oxidized to sulfate. You can see when it's more polluted, the oxidation rate seems to increase. So we use the isotopes to constrain the relative importance of ozone, hydrogen peroxide, and everything else, which is isotopically indistinguishable. And the only thing that we can really constrain well with the isotopes observations alone is ozone, because it has such a high O17 excess signature. So we can constrain that within a pretty narrow range of between 2 and 9% of total sulfate formation. However, we can utilize the pH dependence of the ozone reaction to say something about the other oxidation pathways. So this is an example. This is a calculated sulfate production rate during kind of typical conditions during our observation period as a function of pH for 4 heterogeneous sulfate formation mechanisms: ozone, NO2, hydrogen peroxide, and transition metals. And so at a pH, let's say, of around 4, ozone won't be very important, and so you would expect a low O17 excess value, which is the dotted black line. And higher pH, which has been suggested by some studies, would result in a much higher O17 excess value. And at higher pH, you would also expect NO2, for example, to be important. So you can already kind of see some of our conclusions from this is that given our constrained low importance of ozone, likely NO2 is also pretty low in importance. So we use a GSChem version 10, a nested grid during the time period of the observations, and Jingwen has implemented these 4 heterogeneous oxidation pathways into the model, explicitly calculating their formation rate as a function of aerosol pH that's calculated from isoropia. So this shows the standard model without these heterogeneous sulfate formation pathways. The left shows the sulfate concentrations at the surface during the campaign, and the pie chart show the sulfate production mechanisms during polluted and clean conditions. So the first thing to note during clean conditions, the dominant type of sulfate is actually primary anthropogenic sulfate, despite the fact that it represents only a few percent of total sulfur emissions. And that's indicative of the slow oxidation rate of SO2 in the model. During polluted conditions, we have a lot more secondary sulfate, and most of that secondary sulfate is actually forming from gas phase oxidation by OH. This was a bit surprising to me. The reason why is because during polluted events, you get a lot of HONO from the heterogeneous uptake of NO2 in the model. You also see a lot of HONO in the observations. This shows the comparison with the isotopes. And you can see the model is underestimating the observed isotopes, suggesting an underestimate of ozone oxidation. So this is after Jingwen implemented the 4 heterogeneous production mechanisms. And in both polluted and clean conditions, it represents about 20% of total sulfate formation. And the smaller pie charts show the 4 different heterogeneous production mechanisms. And we calculate that the transition metal pathway dominates due to the relatively low pH that we're calculating in this region. However, ozone is about 20% of sulfate production, and this does result in an increase in the modeled O17 excess, but most of the model simulation underestimates the observed isotopes, suggesting that we're still underestimating ozone oxidation a bit. This shows a time series of modeled and observed PM2.5, sulfate, and the sulfur oxidation ratio. Even after adding these 4 heterogeneous sulfate production pathways, there's some improvement in the underestimates, but the model still does underestimate all 3 of these metrics. So the underestimate of ozone oxidation could be because we're slightly underestimating the aerosol pH, but we hypothesize that the underestimate is due in large part to the fact that the model does not have a sulfate formation on alkaline dust. Now it does in the standard version now as a switch, I think, but back in version 10 it wasn't there. So fresh dust is alkaline, and so it will result in a high O17 excess value for sulfate that forms on that dust. And we calculate that just 9% of total sulfate abundance would need to form on alkaline dust in order to resolve the discrepancy in the isotopes. So not very much. And this is actually consistent with earlier work done by Duncan Fairley, who calculated that about 10% of total sulfate in the Beijing area is from sulfate formation on alkaline dust. So in conclusion, our calculations suggest that about 20% of sulfate abundance originates from heterogeneous sulfate formation, and that we calculate that the transition metal ion pathway is dominant. However, I'd like to note that this is highly uncertain because of the uncertain concentrations of dissolved metals. We would need sulfate production on the order of 10% on externally mixed alkaline dust aerosol to resolve the discrepancies in the isotopes. However, this still would not be able to resolve the model's low bias and sulfate concentration and sulfur oxidation ratio, suggesting that we need another mechanism to explain this discrepancy. Based on the observations of the oxygen 17 excess, NO2, heterogeneous NO2 oxidation is negligible and can be neglected in models. And that's it. Thanks for your attention.
Primary sulfate, 3% is pretty arbitrary, and it's really more subgrid sulfate. And from what we looked at, when it's only gas phase, it's hard to get that over 1%, like when we were looking at formation of influence. So I suspect when you get actually 3% primary sulfate, it must come through subgrid aqueous bond. I'm wondering if that could help get you to the O17 ratio if some of that primary sulfate, subgrid sulfate, was actually through ozone.
I mean, in like a plume itself, like a smokestack.
It's not really primary.
So people have done actually isotope measurements of what kind of comes out of a plume from, I think, a coal-fired power plant, and the value is basically 0 per mil. So
Depends on whether it was later. Like
if it's in the plume,
it mixes into a cloud, it could be.
sure, yeah. If it was immediately processed within a cloud, I guess I would still consider that secondary sulfate if it was outside of this.
3%, like, what are you talking about?
Yeah, I mean, it would depend on the pH. Yeah, for ozone. That's the main determinant for ozone. Yeah, you'd have to have a pH of above 5 to 5.5 above that in order to have significant amounts of ozone oxidation. Yeah.
Other questions, Becky?
Mary, is there anything you can do about changing when or where you sample to try to identify the effect of the dust in the observations to see if when there's less of an influence, the model is doing better to confirm your?
So we have to collect for a while. I think the collection period is about 12 hours. So we have looked into that a little bit. It was hard to tell. There's also anthropogenic dust, so that might be difficult. We have looked at regionally, the amount of dust varies, and I can't remember the region, but a colleague of mine measured in a different region and saw higher O17 excess values, which is actually consistent with a region where there's more dust. So potentially, but I haven't really robustly looked into that.
Okay, great. Thanks, Becky. So our next speaker is going to be 222.
The metals I'm going to talk about now make up less than 1% of PM2.5 mass. But just that 1% can make a huge difference to the environment and to our health. Metals in the atmosphere can catalyze sulfate formation and affect gas particle partition, as you've just heard from Becky's presentation. They can also produce the OH radical, which is the most important oxidant in the atmosphere. If the OH production occurs in our bodies, when metals travel with PM2.5 to get into the lung, they can accelerate the aging of cells, leading to inflammation and neurodegenerative diseases. Airborne metals can also be transferred to the surface, where heavy metals could potentially contaminate soil and the ocean. To estimate all the influences that metals have on the environment and health, we present an initial simulation of trace metals in PM2.5 using the GSCAM model. Oops. This is the overall scheme of metal simulations that we implement in this in the model. We simulate 8 crustal elements and 4 heavy metals. Emissions of crustal elements are dominated by dust sources, either natural dust or anthropogenic fugitive dust. Heavy metals come primarily from industrial activities. The dry deposition process for metals is the same for other aerosols, so we use the default scheme in the model. Wet deposition depends on the solubility of metals. But our sensitivity simulation suggested that whether treating metals with high solubility as sulfate or with low solubility as dust ended up very similar metal surface concentrations and deposition fluxes. So since it doesn't really matter, we choose to use dust scavenging in metal simulations. Chemical reactions of metals in the atmosphere are not considered here because they won't affect the mass of metal elements. As you've probably noticed that most of the processes here are default in the model, except for emissions that are unique to metals. So I'll explain more about metal emissions. Seesaw is a natural source for magnesium, potassium, and calcium. Mineral dust is an important source for all the metals we simulate. We use the model DFOS simulation of seesaw and dust combined with metal fractions in the sources to estimate the amount of metals from seesaw and dust. Biomass burning is a unique source for potassium. We implement the emission factors of potassium from various vegetation types to estimate potassium emissions from biomass burning. Anthropogenic emissions for the states are from the NADA inventory, which is essentially the NEI emission, but with more metals available in NADA. Anthropogenic emissions for Canada are not available in existing inventories, so we create our own emissions. Crustal elements are estimated from a global anthropogenic fugitive combustion and industrial dust inventory, along with metal fractions in dust from observations. Heavy metals are estimated from elemental carbon emissions for Canada, along with heavy metals to EC emission ratios in the NADA inventory. So now we have anthropogenic and natural emissions along with deposition processes for metals. We can simulate for metal concentrations and constrain by observations. This is showing the annual median concentrations of crustal elements in PM2.5. Circles being observations and backgrounds being simulated concentrations at a quarter degree. The spatial distribution of crustal elements are primarily driven by dust emissions, as shown in the pie chart. Enhanced concentrations over the eastern states, over the central US, especially for silicon, aluminum, iron, and calcium, is due to anthropogenic dust from agricultural soil. Hotspots over the southwestern states are due to natural dust emissions. In fact, to match with observation concentrations, we have reduced anthropogenic dust emissions by 50% and doubled natural dust emissions in the simulation presented here. Then this is similarly showing concentrations of potassium, magnesium, and PM2.5. Potassium distribution reflects its biomass burning emissions, which is high over the southeastern states. Magnesium distribution is driven by seesaw aerosol along the coastline. Then this is showing concentrations of heavy metals in PM2.5. Because anthropogenic emissions are their primary sources, we see enhanced concentrations of heavy metals over eastern states where industry and power plants are dense. Still, to match with observations, we have increased anthropogenic emissions of lead and arsenic by 5 times, which is a considerable amount, likely reflecting missing sources such as trash burning or the resuspension of legacy heavy metals in soil from historical activities. So as you've noticed that we have to make a lot of revisions to the original emissions, which reflects our knowledge gap in the atmosphere processes of metals. Despite the deficiencies, this metal simulation still provides an exciting starting point for many future applications, such as the health effects of metals in PM2.5, the effect of metals to atmospheric chemistry like sulfate formation, SOA formation. We can also use this simulation to estimate the airborne metal deposition to soil and the ocean, which is concern for the environment. So as a summary, this metal simulation is in an early stage. There are lots of potentials for future developments and applications. You're welcome to continue the efforts to reach the full potential of metal simulations. Thank you. And before that, a special thanks to my co-authors. Sorry, I forgot to have their names on the slide. They're Vental Martin, my supervisor, and Jim Meng from our group, and Baron Henderson from EPA, along with other EPA folks who contribute to this work. Thank you very much.
Other questions? Oh, sorry.
I recently noticed that several Southern California counties fell out of compliance for lead tax standards, and I noticed in your plot you did have a spike in lead deposition in Southern California. Do you know what source is driving that in your simulation?
In the south, can you see it? Sorry.
In the southern part of California.
Did you say that there's a decline trend in lead?
and you had a local maximum in lead. I was curious if you knew what the source of that was.
There are some local sources that could be driven by some local industrial activities where the mining processes. There are some, you'll see some other other hotspots in heavy metals that we cannot resolve in the simulation. There could be something locally that affecting the measurements and we're not capturing. Also, I'm not quite sure. I'm not very certain about the measurements as well, because most of the heavy metal measurements that we use are below detection limit. So the data we're using are not does not have a huge quantity. So I think there's probably uncertainties in both modeling and observations.
To the back.
So I think in the default version of GeoSchem, there's an assumption that dust is like 3% calcium and 5.5% magnesium. I was wondering how far off are those assumptions compared to what you would in your simulation?
Well, I don't remember exactly what the percent I have in my slides, but my percent of metals in dust is based on the improved observations at Arizona, which is a very dusty region.
Great, so let's thank you again. The next speaker is Will Porter from University of California, Riverside.
Good morning, everybody. I'm here to present some work that I've been doing along with my collaborators, Jose Jimenez and Kelly Barsanti. And this particular project was driven by a desire to it's kind of a meta-analysis of this symbiotic relationship that we all know and love between measurements and models. And as modelers, as geochem modelers, we, of course, depend on parameterizations from measurements, chamber studies, things that are made in the field. And all these things go into many of the pieces, the components of our model, which then, of course, we compare again to observations as a way to see how good we're doing as modelers. However, we can also use the same model output to kind of go back and look at where these numbers came from. So we can do this in a way not only of looking at what should go into our model and taking these numbers from measurements, but also feeding back and comparing the situations, comparing the parameters that went into those chamber studies that we see in our model output as a way to kind of do kind of the circular comparison of what's going into both the studies that feed our models, and then what our models say about what the ambient parameters should be for those same parameters that were generated. So as geochem modelers, what we're kind of asking in this particular project is basically, are we comparing apples to apples? When we're looking at the kinds of things that we're ingesting in our model, are those parameters coming from a space that's similar to what, again, is showing up in our model? So comparing these domains of relevance. And I'm going to start with one that I think is fairly straightforward that we're all pretty familiar with, and just to look at, but we know is important for these kinds of SOA parameterizations, which is temperature. And temperature, this should be fairly familiar. These were modeled for 2013 in January and July. This is on version 12.3. And we see, of course, we have our differences in summer and winter behaviors. And if we look at this in terms of distributions, we can then see kind of a pretty widespread across this area of temperature. I also put in here, this is less interesting for the temperature plots, but they'll reappear for other ones later. I also have vertical lines here, a blue line for the mean daily minimum across our domain, and then a red line for the mean daily maximum. And then we're split by hemisphere on the left and the right, this axis, and then January and July to look at our different kind of modeling regimes. The distributions themselves we also divided up by how much OA we are seeing in that particular grid cell. So for the light shaded, those are going to be the areas where we divided at 0.5 micrograms per cubic meter. And we can see that for temperature, it's fairly well distributed across that. We don't see a huge temperature effect as far as where we have the higher loadings versus the lower. But this is kind of an interesting kind of snapshot of a variable that we know is important. We can also look at this just over the land areas alone. We also know there's big differences vertically. And so as we go upwards in our model simulation, the lightest blue here is going to be our surface grid cell area. And then the darker blue is going to be just going up to where we estimate the PBL is at, which is, of course, a whole other question, but we'll ignore that for now. And then above that, going into the free troposphere. And, of course, we see this drop in temperature as we move upwards through our atmosphere. And then finally, thinking about relevance is not just about looking at averaged over the entire land masses. If we're talking about people, we're also interested in where people are. So we can weight this by where people actually are living. And we see, of course, now we get a big change where people don't tend to like to live in areas that average -20. And so we have this strong shift upwards as far as where people are actually at. And so we get a different kind of relevance when we're looking at temperature, where people are actually living. And again, we have a split where we masked by where we actually have OA greater than 0.5 micrograms per cubic meter. And perhaps more interesting than this temperature snapshot is if we then move on to another important variable, and this has come up a number of times, and I think it probably will again today, and that is humidity. So we know that humidity is going to be very important